Hello. In this video, we are going to look at the acidity of three types of hydrocarbons: alkanes, alkenes, and alkynes in the gas phase. Here is the simplest alkane. In American English, we call it methane, and in British English, they call it methane. Importantly, carbon has 4 bonds, so the carbon is going to be sp3 hybridized. That is the typical hybridization for carbon in alkanes. This video concerns the acidity of various hydrocarbons, and there's 2 different ways to think about acidity. One way is to think about the equilibrium constant for the following reaction. So we have our unaltered methane molecule to the left, and it reacts in such a way that it loses a proton. Leaving the conjugate base, the methyl anion, and a free proton. So we can do it in terms of the equilibrium constant, which is a common way to do it. In this video, we are going to use the other way, and we're going to compute the enthalpy of this particular reaction. So the reaction to turn the neutral compound into a proton and the conjugate base. In the following slides, you will see the computed parameters for this reaction for methane. The next alkane in the series is ethane, which has this structure. When it acts as an acid, it gives up a proton and leaves behind the ethyl anion as the conjugate base. Plus a proton. Here we're emphasizing this particular lone pair by drawing the Lewis dots and drawing them in red. One way to think about the strength of the neutral molecule as an acid is to think of the converse problem about how strong of a base the conjugate base is, how available this lone pair is to share with a proton. And we see from computation and from general experience that alkanes are incredibly weak acids, which means that the conjugate base here is an extremely strong base. The next alkane in the series is propane, which has this structure. When it acts as an acid, we know that we're going to generate the conjugate base, the propyl anion, and we can draw the structure this way. And note that for the series that we're doing here, we're always removing the proton from the primary carbon. So you would get different effects if we were to remove, for example, a secondary hydrogen. But we're just sticking to the primary hydrogen for consistency in comparison. So when it acts as an acid, we form this conjugate base, and we give up a proton. please see the following series of diagrams for the computed parameters for propane acting like an acid, and you can see the action in 3 dimensions, which is the more realistic way to look at it. Even though we write things in a 2-dimensional way conveniently on the blackboard, reality takes place in 3 dimensions. The fourth and final alkane that we're going to look at in this video is butane, specifically N-butane, where N stands for normal, the straight-chain butane. When N-butane acts like an acid, we have the following conjugate base formed: the butyl anion, we have the lone pair, 1 carbon. Recall again that each of the carbons in N-butane is sp3 hybridized. And we have loss of the proton. This particular anion is important because this same anion is critical to the functioning of N-butyllithium, an extremely important organolithium compound. And because this is exactly the same anion that we find in N-butyllithium, we realize since N-butane is an extremely weak acid, that this N-butyl anion, whether formed directly from the acid or from the organolithium compound, is going to be an extremely strong base with all the effects that we would expect from that. Please see the following diagrams to see the action of N-butane as an acid in the gas phase, see all the relevant parameters as computed using electronic structure calculations, and then after that, take a look at the table where we have tabulated the enthalpies of the reactions for methane, ethane, propane, and N-butane in the gas phase, and see relatively small changes in the value, but how large in magnitude it is, showing that this is an enthalpically unfavored process. In other words, extremely difficult. It's a very poor acid. Here is the simplest of the alkenes, ethylene. And we would like to compare the acidity of alkenes with the acidity of alkanes. One of the things to notice right away is that the lone pair that's attached to the hydrogen that we were wanting to see if it's acidic or not, this particular lone pair is in an orbital that is sp2 hybridized, whereas the equivalent lone pair in an alkane is in an sp3 hybridized orbital. One thing to notice when you're comparing sp, sp2, sp3 hybrids to each other is that the bigger the exponent on the p, the more p character we say that the orbital has. Remember that p orbitals are somewhat dumbbell shaped, so the electron tends to be further away from the nucleus, less tightly held than in an s orbital. So the sp3 hybrids will have the most p character, so they will be the most weakly held. The sp2 has slightly less p character, so therefore it has more s character. It is more tightly bound to the carbon atom. And then finally we'll see that an sp hybrid has the most s character, so it will hold this lone pair the most tightly to the carbon atom, and it will be less available for sharing. So let's see ethylene as an acid. It acts as we'd expect, by the formal definition of acidity. And we have the loss of the hydrogen. And we've been color coding the hydrogen atoms in blue just to show the acidic hydrogen, so we can see where it's come from. And we know that we have to have the negatively charged conjugate base. As a hint, whenever you're writing acid-base reactions or any chemical reaction, always be sure that the charge is balanced. We start on the left-hand side with a 0 charge, so that means the right-hand side has to have a 0 charge as well. Please see the following diagrams to see the computed parameters for ethylene acting like an acid in the gas phase. The next alkene in our series is propylene, also called propene. Notice here that this carbon is sp2 hybridized, and this is the particular carbon whose acidity we're going to be examining. But also note that this carbon here is also sp2 hybridized, and that this carbon, since it's singly bound to the neighboring carbon, is sp3 hybridized. So in this particular molecule, we're only looking at the acidity of the sp2 hybridized carbon that's at the end, the primary carbon. When propylene acts like an acid at this particular location, we end up with the expected conjugate base. And we'll see in the table, see further down in the video, that even though this is still a hydrocarbon, because of the sp2 hybridization, this alkene is a stronger acid than the corresponding alkane. So in general, alkenes are slightly more acidic than alkanes because of the nature of the lone pair that's left in the conjugate base when the alkene acts like an acid. Our first and simplest alkyne is acetylene, called in the IUPAC system ethyne, and we're going to see that this carbon is sp hybridized, and we'll see in the three-dimensional diagrams that this is a linear molecule, which is what we'd expect for sp hybridization. We would expect trigonal planar 120-degree angles for sp2 hybridized carbon, and we would expect a 109.5 degree bond angles for sp3 hybridized carbon. So when this acts as an acid, we are left with the acetylide anion behind, plus H+. Now the acidity of alkynes is incredibly useful synthetically, because while this is a weak acid, which means that the conjugate base is a strong base, it's a strong base that's an excellent nucleophile. even more importantly, it's an excellent nucleophile that brings a 2-carbon piece into the new molecule. So if you want to extend the chain of a compound by 2 carbons, an excellent way to do it is to make use of the acidity of acetylene. This hydrogen can be removed in liquid ammonia by sodium. So it's possible in a synthetically useful way to abstract this hydrogen, to make use of the acidity of acetylene, to generate this conjugate base anion, which is an excellent nucleophile that is synthetically useful. Please see the following diagrams for the 3-dimensional structures and parameters for acetylene and the acetylide ion. The next alkyne that we want to look at is propane. So here we have a 3-carbon alkyne. And again, we notice that for sake of convenience, we've color-coded the acidic hydrogen in blue. And this particular carbon here is sp hybridized, as is the other member of the carbon-carbon triple bond. The carbon at the end, again, we have a case where this one is sp3 hybridized. And we're not looking specifically at the acidity of any of the hydrogens at this end of the molecule. We're just looking at the sp hybridized terminal end. So when it acts as an acid, what do we get? We get our conjugate base, which we know has to be negatively charged, and with a -1 charge. We have our lone pair, and we have the H+. So again, as in acetylene, this hydrogen is synthetically abstractable in ammonia solution. It's sufficiently acidic that we can remove this hydrogen to generate this anion, which again is going to be an excellent nucleophile because it's very strongly basic. Part of the reason why this is as acidic as it is this lone pair, being in an sp orbital, is more tightly held by carbon, so it's less available to share with the hydrogen. Please see the following table, which summarizes the enthalpies of loss of a proton by the various classes of compounds, alkanes, alkenes, and alkynes, showing that alkynes are the most acidic. I thank you very much for your attention, and as always, have a good one.